Audio check. I hope you all can hear me. I'm on a new computer system and I just got yet a second new computer and I will be getting a third one. I'm trying to overhaul my computer apparatus. Patrick Alexander observed that jet. I love that jet, the XB-70. It debuted in the early 1960s. It was in development in the 1950s. It was the fastest bomber, and nothing could catch it. It's just such a beautiful machine, and that's why I show it a lot. So I'm on Streamlabs right now. Normally on StreamYard I can take comments from the comment section and put them across the screen. I can't do it, so I'm just going to say hi to Patrick Alexander and Mats. Thank you so much for visiting. And Mats has to hit the sack. Yes, I'm a night owl. You all know that. I keep strange hours. Thank you for joining us here. Glory and honor to our Lord and Savior Jesus Christ. This show is dedicated to Him. The Evidence Reasons Academy really does explore a lot of scientific topics just to kind of help us understand science. Some people will say, well, what's the point of some of these ventures into deep academia? Well, this is kind of my version of reality TV. What's it like to be a professional creationist researcher? You're going to see what it's like, where we sometimes just dig into stuff that is just so tedious and boring and insufferable, but it's a cross we bear. And sometimes in the process, you learn something, and sometimes, to quote Edison, he says, I haven't failed at finding the light bulb. I succeeded in finding 10,000 ways that won't work. So sometimes I'm going to just explore a topic that I think is relevant, and it may not have any immediate benefit, but sometimes it will lead to something down the line, and that's just the way it is in professional creationist research. And part of that also is learning basic science. I was actually, by this time, supposed to be in a PhD program that fell through, but one can continue learning, and there's just a lot of stuff online. A lot of what I'm covering now here on the Evidence Reason Academy is kind of like what I might be studying as a PhD graduate student. So, one in photonics. But who knows, maybe I won't get a position in photonics. It might be in bioinformatics. Who knows at this point. I got offered a PhD position at Liberty University, but I'll have to pay my way through. So that's something I have to decide whether I'm going to pursue that. In the meantime, I'm trying to get a number of opportunities started up, including a television contract. And it will be forthcoming, the details. I'm kind of mum on it right now. So what is the relevance to the Christian faith about the topic we're exploring? The distant starlight problem is very, very, very difficult for young Earth creationists. I was an old Earth creationist because I considered it insurmountable. But when mainstream physics began entertaining variable speed of light, I began that opened a crack in the door for young Earth creationism. So studying the nature of light is going to be very interesting, and then we can begin to entertain how could light speed be variable. So this is where it's headed. And unfortunately, there's a lot of preparatory math just to be able to understand the equations that define classical electromagnetism, which is tied to the speed of light and the nature of light. That's classical. That would be Maxwell's equations, which is good enough for most everyday applications of engineering and science and modern technology. But the more complete theory is quantum electrodynamics, which I hear is very, very hard. We might be able to determine variable speed of light theories using classical, at least get there. I have concluded that the way special relativity has been taught, and then also studying classical electromagnetism, that there has to absolutely be an absolute rest frame, and that not everything is relative. Everything might be relative to something that's absolute. And that intuition has been even strengthened by the fact that quantum mechanics requires absolute time. So not all time is relative. I've argued that clocks can tick at relatively different rates, and we might quote unquote call it an error, but I prefer not to call it an error. It's just an adjustment, a recalibration adjustment. And we can definitely say one object is moving faster than another. Because of the Lorentz transformation, you can tell which one is moving faster relative to the other. That's just like undeniable. It's not a two-way transformation. One guy's clock's going to be faster than the other. This has been proven experimentally. Therefore, that infers an absolute frame. And to be able to actually show that, it's kind of good to actually work out the Lorentz transformation. The Lorentz transformation came about, I'm learning now from my show yesterday, the Michelson-Morley experiment contributed a lot to the formation of the Lorentz transformation that can be applied to Maxwell's original equations of electromagnetism. I have heard indirectly, so take it with a grain of salt, that Maxwell actually was very Newtonian in his views about the speed of light, and that equation was assuming some sort of rest frame in an ether. If there is an ether, then it raises the question, why did we have the Michelson-Morley experiments? Why were the results what they were that suggested there is no absolute rest frame? And it was solved by Lorentz with his Lorentz transformation, but Lorentz transformation actually shows there's an absolute rest frame. You can't run away from it. I can't believe that people are still teaching relativity and saying there's no absolute time. You absolutely see it there, and that would totally agree with quantum mechanics. So that's what I don't quite get. I have studied general relativity. In fact, this was my book, but that was 10 years ago, 10, 11 years ago, and even when I was learning it, it was kind of foggy because general relativity is hard. The notation is just gruesome. I'm just like, they have stuff that is just like you don't see anywhere else. There's just like this tensor notation is just brutal. So guys, I don't think this will be the most spiritually uplifting, like say a sermon. This can be downright tedious and degrading, but it's a cross to bear. So let's just get to it. I'm going to derive, to be able to derive the Lorentz transformation, to prove it is a good transformation for Maxwell's equations. We have to learn the electromagnetic wave equation and also this thing called the D'Alembert. That was the thumbnail I had was of D'Alembert. Let me see if I can, let me see if I can get my screen capture here going. So that thumbnail is of D'Alembert there. Let me see if I can get a better picture of him. D'Alembert, from which we get the name D'Alembertian. So let me just show him. He looks like a happy guy. Let's see if I get a bigger picture of D'Alembert. There we go. That's D'Alembert. Okay, so now the heavy lifting starts. Let's start with Maxwell's equations. Maxwell's equations of electrodynamics. I have said this is real science, guys. This is why, if you want to know I have a real bad attitude about evolutionary theory, you compare it to real sciences and real theories like classical electromagnetism. I mean, this is just, it's beautiful, it's powerful, it actually works, which is more than I could say for evolutionary theory. So this is how I developed a really bad attitude. And these evolutionary biologists are opining what a good theory is, and I'm just like, no, it's a terrible theory. It doesn't agree with physics, chemistry, and statistics. It's just, and yet and it doesn't have experiments. You compare that to electromagnetic theory, that's a real theory. And why is it that, unfortunately, Darwin's name is more well known than Maxwell? Maxwell has done more to usher in the modern world. Darwin has done nothing, virtually nothing by comparison, except to come up with a theory that has affected our society, but it's certainly not affected our understanding of science in a positive way. It's actually impeded our understanding, and it's been mostly damaging to science, and I'll argue damaging to society on the whole. So let's just move forward. And there we go. Maxwell's equations. And so we had covered the divergence operator, and that's kind of nice. And then we had the curl operator here. Now I actually learned electromagnetism mostly with a lot with the integral form, and not so much with the differential form. The differential form is a little easier actually to understand. And I wish my book had focused more on the differential form. So now there's a situation, we have this thing called J, this J term in the fourth of Maxwell's equations. That's some sort of electric current. And I should know what that is. Now I'm embarrassed. Ampere Maxwell law, which is the fourth equation. Let's just look at what this is. This is the electric current density vector, that J, and that's the magnetic permeability of free space. Okay, so let's go back to, now we settled that. The electric current density vector. Was that right? The electric current density. Now I want to go back. Ampere Maxwell law. That is the electric current density vector. Electric current density vector. Electric current density vector. Okay, I've rarely gone this far. I mean, I need to do some exercises where I work with the second equation. This one's relatively easy. That's the first one that we do, is Gauss's law. I'm not so good at this one at all. Can forget that I really understand this or this. But one way to learn is by studying. And so we're going to do that. We're going to study the electromagnetic wave equation. So let me see if I can bring that up. So let's just go through and read it. And let me see if I have any comments here. Okay, no comments. All right. The electromagnetic wave equation is a second-order partial differential equation that describes the propagation of electromagnetic waves through a medium or in a vacuum. It is a three-dimensional form of the wave equation. The homogeneous form of the equation, written in terms of either the electric field or the magnetic field, takes the form that you see there. I'm not going to read that. So this is velocity. VPH is the photon speed. That's the Laplacian. And this is the second order derivative. It can be applied either to the electric or magnetic field. VPH, yeah, velocity of the photon, 1 over the square root of mu times E. V photon is the speed of light. I don't know why they used V photon. They could have used C. Okay, that's why, because the speed of light is dependent on the medium. And this is a general equation that will even apply through light going through glass. So, okay, that makes sense. This is the Laplace operator, and the velocity of the photon is about 300,000 meters per second squared, a fundamental physical constant. The electromagnetic wave equation derives from Maxwell's equation. In most older literature, B is called the magnetic flux density or magnetic induction. So the magnetic flux density or magnetic induction. They don't call it the magnetic field, do they call that? Okay, the magnetic field could also be called the magnetic flux density or the magnetic induction. So the modern term is magnetic field. The following equations of the divergence of E equals 0, the divergence of B equals 0, predicate that any electromagnetic wave must be a transverse wave, which I don't know what that means, where the electric field E and the magnetic field B are both perpendicular to the direction of wave propagation. Transverse. Okay, they're a transverse wave, so it propagates in one direction, but the wave is perpendicular to that direction. I need to point out something. You see this divergence of E equals 0? I need to point out something. Maxwell's equations do not have that as stated. So you could see it right here. Divergence of E is actually supposed to be rho over epsilon naught. But if we have a charge-free environment, you can set it to 0. The divergence of B is always equal to 0. But that's not the case for the divergence of E. What we're deliberately doing is we're taking a situation where there's no charge, and if you don't have any charge, I don't think you have any current. And so this will become 0 here. And this is how we can get the situation where the curl, let me show it to you. Okay, here, yeah, the curl is equal to this. The curl of the curl of B is equal to this. So now let me look at Maxwell's equations again. So we have this term, so if you zero this out, and then you zero that out, you'll get this, like that. And there's a little trick here that they do. There's something else I wanted to mention. Maxwell's equations, and anyone correct me if I'm wrong, are first order partial differential equations. Maxwell's equations are first order partial differential equations. The funny thing is, if you want a solution to this, you do this kind of these math tricks, you end up with a second order differential equation. You're like, well, that's not going the right way. You're supposed to come up with the direct equation. And it's a little more subtle than that. You actually take the first order partial differential equation, the solution's a second order partial differential equation. And let me just make sure I got it right. Yeah, you get a second order partial differential equation. No, you get a second order. Let me look at this. Yeah, you get a second order partial differential equation, and you're going the wrong direction. But it turns out you can then it can, from the second order equation, you can find out that that general solution would include things like sine waves, which is very nice. Electrical engineers love sine waves. So this complicated equation, one very nice solution is the sine wave. There are other complicated solutions beyond the sine wave, but when you can have a sine wave or sum of sine waves, you get to describe a lot of solutions to the wave equation, which is great. And that's how we're able to transmit. That is how we're able to transmit all sorts of things, like we modulate a sound wave into electromagnetic waves and then demodulate it, because some of these sine waves can make other waveforms, and that's a very nice. That's very nice. That's a very nice property. So, I mean, that's known because of the Fourier transform. So anyway, let's look. Let's just go through this derivation. What else did I want to say? All right, that's mostly what I wanted to say. These are special conditions. I'll read it. In his 1865 paper titled A Dynamical Theory of the Electromagnetic Field, James Clerk Maxwell utilized the correction to Ampere's circuital law that he had made in Part 3 of his 1861 paper on physical lines of force. In Part 4 of his 1864 paper titled Electromagnetic Theory of Light, Maxwell combined displacement current with some of the other equations of electromagnetism, and he obtained a wave equation with a speed equal to the speed of light. He commented, "The agreement of the results seems to show that light and magnetism are affections of the same substance." The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. And there you have it. That's the money insight right there. Magnetism, electricity, and light, all connected. That was not known until Maxwell's insight. Maxwell's derivation of the electromagnetic wave equation has been replaced in modern physics education by a much less cumbersome method involving combining the corrected version of Ampere's circuital law with Faraday's law of induction. This was much more brutal before we had the simplifications. How Maxwell did this is amazing. And let me see if there was a postcard here. Maybe you take a look at. It's worth it to look at the postcard. So Maxwell wrote a postcard, and you could see how he was trying to describe his theory of electromagnetism and his theory of electromagnetism and how it was tied to light. So it's just amazing. I'm glad they preserved that postcard. All right. To obtain the electromagnetic wave equation in a vacuum using the modern method, we begin with the modern Heaviside form of Maxwell's equations. And the Heaviside form is the one that I've typically showed like this. This is the Heaviside form of the equations. Because Maxwell originally had 20 equations and Heaviside reduced them to 4. In a vacuum and charge-free space, these equations are stated as this. Lots of zeros, which makes it nice. We love zeros in an equation. So there's no current term here, which is great. That makes it easier. These are the general Maxwell equations, specialized to the case with charge and current both set to 0. Taking the curl of the curl equations, the curl of E yields B, the curl of B, which is equal to this second order derivative here. Okay, so you get the curl of B. So the curl of E can also be taken as the curl of, so we take the curl of E is this, therefore the curl of this Alright, so if we take this here, and I wish I had some way of highlighting. I don't know if there's a way I can overlay a highlight. I'm going to have, maybe I can ask Johnny B tomorrow when we talk his calculus paper. You see right here is equal to this second equation here, and you could replace it. And so then this goes in here. And then if we take the curl of that, I guess you can take the partial derivative out, and then this, you can interchange the two terms. I will point out when we're interchanging the order of differentiation, that can only be done if the Schwarz conditions are satisfied. So I think they're assuming you can do that. In general, you should be careful to not do that unless you're sure. So the legitimacy of this operation from going from here to here, I think it requires a little care. I'm just pointing that out. I'm trying to remind myself, you can't just plain flip it. You could get in trouble. If I'm understanding Schwarz's theorem. Let me see if I could find it. Schwarz's theorem. Schwarz. It's called the symmetry of second derivatives. Schwarz's theorem. We can do this. We can flip the order of differentiation under certain conditions. Okay, so this operation here, it presumes that the Schwarz's conditions are satisfied. Just pointing that out, because this curl operator is a differentiation. Okay, so this is a pretty clever trick, that the curl of B equals that, and the curl of the curl. So if we put this here, take this equation here, we can substitute this with that from here, and then we get this. And then there's a vector identity. I don't know what they call this. Sometimes they'll name the identity. Let me see if there's a name for this one. The curl of the curl. Let's see, vector identity. It's just the curl of the curl is the vector Laplacian operating on the vector field A. It's the curl of the curl theorem. All right. Going back. This is tedious. So we could either start this as the starting point or this at this starting point, and we end up with the Laplacian. The curl of the curl equals a Laplacian. Oh boy, now I'm a little stuck. How do we get this equation unless we assume this is 0? Okay, so the divergence of this is 0 and the del of 0 is 0. I'm confused. I don't know how we get this. This is, okay, I'm sorry. This term here can also be described this way. Okay, that's the Laplacian here. That's the Laplacian. I don't know what we do about this term. That's what is disconcerting. Since this is equal to 0, if we put E where the V is, or B where the V is, this will be 0, and this all becomes 0, and then so you get a minus the Laplacian of E or V. And that's exactly what happens here. That's the derivation. Oh my goodness, this is painful. Okay, I need to find out how I can draw colors and connect it, because that would make it clearer. So if I do a slideshow, I can do that. All right, so this is how we get this form of the equation. This is the electromagnetic wave equation. And you could see you can either use E or B. It has the same form, which is really nice. The C squared, C naught squared can be derived from C naught, which is that figure. And that's all we need. Now the way, if you could see it, if you take, let me see if I could try to show this. And I hope they don't give one that's just miserably difficult. All right. So let me just show how this becomes a D'Alembert. If you factor out E, you can get this operator here. You see that? So there's a way to state this. You just make an operator that's defined this way, and you can apply it to E or B. And that's the D'Alembert. So the D'Alembert is composed of this term here minus the Laplacian. So minus this operator here. This you take the D'Alembert is composed of this operator minus the Laplacian. So this is the yeah, there it is. And so that's the D'Alembert. And unfortunately, that's a scalar Laplacian. Okay, this is where it's going to get a little confusing, unfortunately. this here is the vector, this vector identity, the curl of the curl. I think this is, they call that a vector Laplacian, but it's really a scalar Laplacian operating on a vector. Let me just verify that. The vector Laplacian, I get confused with the... No, it's not the vector Laplacian, it's a scalar Laplacian. The scalar Laplacian is much simpler. Scalar. See if they have it. The scalar Laplacian is simpler. Yeah, that's a scalar Laplacian. So I think the Wikipedia entry is off. I don't think it's correct. So that's just my opinion. And let me just look again at this. The curl of a curl. Now that's a scalar Laplacian. This is a scalar Laplacian, not a vector Laplacian. And then we look at the vector Laplacian. We look at the vector Laplacian one more time. Oh, that wasn't helpful. Del of that. Okay, that's the vector Laplacian. Yeah, this is the okay, I gotta take exception. This whole thing here is the vector Laplacian. This is the scalar Laplacian applied to a vector. It's a little confusing. Let me just verify that. I think this could be very confusing. Electric current density vector. Okay, so this is curl of a curl. Maybe a vector Laplacian does work that way. The curl of a curl of A. So let's compare. Apologies, everyone. So we have the Laplace operator. Hang on. We're almost done tonight. This is enough. So okay. Let me just move some stuff over. Settle this in my mind. This is bothering me a little bit. So in one case the symbol is V, the other is A. We can work around that, right? So the curl, we add it to that side. We add this to that side. Okay, I've read some literature that it's really a scalar, this is a scalar Laplacian here. Anyway, the nice thing is it's defined nicely how to do this operator. I'm not going to worry this too much about that. You can apply, it's very simple here. I'm just going to show it. The Laplacian operator, little aggravating. See, there it is. The Cartesian one is particularly easy. Which you're supposed to recover a vector after you have completed it. Vector, a scalar Laplacian, and you reconstruct a vector. Okay, so I'm just gonna, I'm sorry. Let me show what I was what I was looking at. So you can add the Laplacian to both sides, and you're supposed to get a vector on each side. Let me go now to my, I'm going to look at something here. I'm pretty sure you're supposed to end up with a vector. And we're almost done. Yep, you get a vector. Should get a vector. I think it's a vector. Pretty sure it's a vector. I actually don't know. Now I'm a little confused whether you end up with a vector or not. In any way, you're taking a partial derivative of that. When you take the partial derivative, you end up with a scale. All right, now I'm really confused. Anyway, when you take that partial derivative, because I don't see that we recover the vectors. Okay, so let's try this again. Okay, the scalar Laplacian of a vector. So I have to get this right because this is really bothering me. Laplacian. Okay, so let's see. Laplacian, scalar Laplacian of the vector. I think I've seen it somewhere. Let's try this. Now I really regret I don't have okay, I'm going to try this. I've seen it before. I swear I've seen it. If the scalar operator, there it is. Vector field. There it is. If the scalar Laplacian is applied to a vector field, it acts on each component and in turn generates a vector field. Can apply the scalar Laplacian to a vector field that acts on each component and generates a vector field. You can apply, but you're supposed to get a vector afterward. So I'm applying a scalar Laplacian and getting a scalar. Okay. Okay. The Laplacian is a scalar operator. But the electric field, see, I'm confused because the electric field is a vector field. It's not a scalar field. See, the electric field is this vector field. Okay, the electric field is defined as a vector field. Okay, so, all right, so now at least I know where the source of my confusion is. We're applying a scalar Laplacian to a vector field. Do we ever apply a vector Laplacian to a vector field? Okay. So you can get a vector, you can create a vector Laplace. A scalar Laplacian applied to a vector field gives you a vector. A scalar Laplacian okay, so a scalar Laplacian makes a vector. A scalar Laplacian applied to a scalar field yields a scalar. A scalar Laplacian applied to a vector field creates a vector field. And since we're taking the second order derivative here with respect to time, that of E and E is defined by the ijk or the x hat, y hat, z hat component vectors, you get a vector field. So you apply the scalar Laplacian to a vector field, you get a vector field. Okay, that's what I think. I could be in big trouble if I'm misteaching that. Anyone is welcome to correct me. But anyway, this has been a grueling session trying to figure out and see if I have we've been live for about an hour and I'm just about done. This is how we start with Maxwell's equation under the condition of no current and no charge, and then you're able to derive a second order differential equation which doesn't even look like a solution because you're going the wrong way. You're trying to remove the derivative, but that's okay. Just to round this out, going back to the to this here, somewhere it will say that you start to get a solution to that second order equation will be the form of sine waves, which everyone really loves. And there you go, there it is. Sine waves, the real part of this e to the I omega t, which generates a combination of sines and cosines. So you take the real part, which will be the cosine And a cosine wave is really, you could say it's a sine wave. Okay. All right, so this is the solution of that second order differential equation. So you take the first order differential equation, you make a second order differential equation, and then you can find specific solutions. I don't know if this one describes the most general, because there are all sorts of strange, there can be other really strange solutions that I seem to recall, where you have a kind of a circular wave solution, which is just bizarre, not a nice simple sine wave. So, and I could be wrong about that. So anyway, that's mostly it, and I'm ready to call it a night. Glory and honor to our Lord and Savior, who helps us bear the cross of what we just went through. And I'm fumbling through this, but as I said, one way to learn something is to try to teach it. And this is what I'd be doing anyway with my evenings, trying to learn electromagnetic theory if I had been in a PhD program. And certainly I'd be spending a lot more time than just 1 or 2 hour afternoons, in the afternoon or evening. I'd be actually working through very specific equations, but this is just good to get the basics underneath, under my belt, and maybe I could work on more specific things. That's if I go into a photonics program, I'll have to learn some of this really well, and it might be worth it for me to go through an electromagnetic theory book like this. I also have Griffith's electromagnetic theory book, and maybe I can work through that. But in any case, thank you all for joining me through this nerd torture session. Take care, and God richly bless you all.